So where we ended yesterday, we started talking about the responses of first and second order systems. And we saw that first order systems, the step response for our first order system was, of course, had two parts, a transient and a steady state response. The transient part was the part that is determined, the behavior of the transient part is determined by the system transfer function. And the steady state part is determined by the input, the signal that you input. And one of the things that we saw is that a first order system couldn't oscillate, right? So you couldn't get a simple first order system couldn't oscillate simply because the solution of first order systems wouldn't give you complex poles or complex solutions where you have a e to the j, e to the minus j omega t, or e to the minus jst appearing, e to the minus jat, sorry, appearing in the time domain answer. We saw though that on the second order systems that wasn't true. And we started looking at a general sort of second order system yesterday, which is what I have up on the screen. So a numerator, it doesn't have any zeros in this particular one. And it's all poles. There are two poles somewhere in here because it's a second order system. And we have two variables inside of here. Sorry, three constants inside of here, which are b, a, 0, and k. Right? The variable, of course, is s. And to solve this now, for where we ended yesterday, is to see what happens for this thing when you put a step input into it. So xs is 1 over s. So up until this point, what we covered yesterday and today, everybody is clear on that? Has been following it so far? Okay. All right. Oh yes, and Sadie, I have an answer for you for that, for your question. And Mario, thank you for the capital letters. I believe so too. It's almost religious. Okay, so to find a solution for this thing, we have to find, was engineering not a religion? Many years ago, yes, we could have a very deep philosophical discussion on that. That is where the term guilds, G-U-I-L-D-S, came in, right? Yeah, right. So the world according to Laplace. So to find the inverse transform of something given like this, of course, you have to resolve it into partial fractions, and you can do it in this case. You just simply apply the what do you call it, the quadratic formula to it, and you get that the answer therefore is going to be composed of three parts: something over s, which is a part that behaves like this step. Get this here, right? So the part that behaves like this step. Then we have this bit here and this bit here. Of course, you can solve for the A, B's, and C's depending on the scenario, but that's kind of irrelevant at this point in time. And what we saw now is that as we change K is the one that is going to determine a lot of this stuff for us, right? Because it's inside of here. And what we saw is that if K is less than 0, first off, once K is less than 0, this is going to give you an e to the answer, however the answer turns out, is going to give you an e to the plus a t kind of behavior, right? So that whatever it is, K is going to give you that. If K happens to be between 0 and minus 1, then inside of here is going to be a complex number. So you're going to get an e to the plus JAT coming inside of here. And as you know, e to a positive complex, this is a complex sinusoid, cosine plus j sine. So this kind of thing, either way, once K is less than 0, it is going to give you an unstable output. In one case, if it is between -1 is less than -1, we saw that the answer would be an increasing exponent. So the answer would look something like that. Or if it is between 0 and -1, that the output answer could give you, if we have a bipolar system, it's going to do something like this. If it's unipolar, it will do something like this and keep increasing until the limits of the system are reached, whatever those limits are. So k less than 0 is not good. K greater than 1, in both cases, you're going to get a stable answer. If it's between 1 and 2, again, somewhere inside of here, you will get, in this case, an e to the minus j something t. All right. This is, again, a complex exponential, but cosine plus j sine, but the minus sign means that whatever it is going to die out. So the answer for that one is going to give you something, just one, right, is going to give you something that will die out eventually. Or if it is greater than -2, it's just going to be a simple decaying exponent. Either one will eventually be stable. Whether this behavior, this kind of oscillating behavior is what you want, is determined by the type of application that you're dealing with. Right, so as I mentioned yesterday, things like a damper system for a vehicle on the suspension system. This is not what you would probably want. It will die out eventually, but it makes the thing unstable. All right, and there are any number of applications like this that you wouldn't want that sort of oscillating behavior, right? Industry, if you're into robotics and you have, for instance, a big crane in a factory, if it's moving some car component from one point to the other, you don't want it swinging back and forth until it eventually settles on the position it's supposed to settle on, right? That would clearly not be good, right? So you need to know that you would probably want this type of behavior. But how fast it settles and so on, that's the purview of control systems. But you understand that in some cases, that is what you would want, not the oscillation, right? And then we were looking at what happens if k is between 1 and 0. And then that is the one that we said requires some extra exploration. And we'll do that by looking at a couple of examples inside of here, just to see what exactly transpires when k is now between 1 and 0. So here is a system, right? I have the standard form of the system here. And then I'm saying, okay, let k equal to -1. A is 2 and b is 4, just arbitrary. So when you do that and you make the substitution, we get the transfer function here, and xs is a step. So you try to get what is the step response for that. So if you put that in there and you either find the inverse or you plot it out, you get something looking like this, right? You could put this into MATLAB, for instance, and ask it to do the response for you. So you get a graph, and clearly, as you see, as the time goes on, the answer just gets bigger and bigger and bigger, and it's going to cap off at some point. So it's proving k less than, what is that? K less than -1, k less than 0, we are unstable. Here now we going the other way, that k is greater than, is positive, and in fact is comfortably positive by picking a value of 3. So a is 2, b is 4, and this is now the transfer function here. So what does the step response for that look like? Put in the step, and here it is. So the step response for it now, remember you put in a unit step. A unit step would be, sorry, where am I? Like this. The unit step would be this. right? So the unit step, right, at 0.1. So the unit step does that, and the system goes up to, it responds, and it settles eventually on a value of 4. So after some period of time, it settles, it stabilizes on a value of 4. Back inside of here. So B is 4. Remember, if we went back early on, go back a couple of slides. Go back here. Right. No, I didn't mention it at this point. Okay. So we'll talk about B in a little while. So you go back here, and right. So we put in a unit step, and the output is responding. In fact, it's responding almost like a first order system. You remember a first order system? You have the transient response, which would be like this up to some point, and then you have the steady state going on after. This is good, this is stable, it will settle on. Whether we want it to settle on 4 is a design issue that you have to address, right? If you wanted it to settle on 1, then okay, you have some things to work on, but at least it is settling down. It's going to be stable. But here, look at what happens here now. Let's take A equal to 2 again, B equal to 4, but we vary K now, and we put K equal to 0.5. So K equal to 0.5, we have the transfer function inside of here, and we put in the step response. Step response now, look at what happens. We have it stable again. So the step response, remember the step response is this. That's the unit step going in. So the system is responding. All right. It goes up. It passes. It eventually settles down at about 4, which is where we the system itself, where it apparently seems to be designed to settle. But notice what is happening here. It has gone over 4. It went up to about 4.5. It comes down to about maybe somewhere here, which looks like at about maybe about a 3.9, 3.8, somewhere here, and then eventually settles. We call that behavior, it's oscillating, and there's an overshoot. So the target was 4, and it has gone past the target, and then it responds and comes back down. All right. Sometimes you're not able to avoid that. In other cases, that will be absolutely disastrous. Okay. Again, just think of like steering a vehicle. If this was that the step response was that you suddenly pull the steering wheel to the left or to the right, right? You wouldn't want the car to respond and then go past where the point where it was supposed to be pointing, and then actually straighten back up and the like, right? Or plane, you're flying a plane, or you know, that those kind of things. You can think of any number of applications where that may not be desirable. And then the next thing now, we decrease K. So we make K 0.2 now. Remember, we're looking to see what happens when K is between 0 and 1. So here it is now. Remember the step. The step is here. All right, so the step has come in 0 to 1, and the system responds, but it's gone considerably higher than 4. It has gone up almost to 7, and it comes back down to 2, and then it goes up and down and goes up and down and so on, and is even more oscillating, more oscillations there before it eventually settles. It looks like in this case after about 30 seconds, right? It's settling down. Let me see what the previous one was. Right, so the previous case is settled down after about 6 seconds, and the earlier one with K equal to 3 settled down after about 18 seconds. So a little bit of fluctuations there in terms of how long it's settling. So this one is oscillating a lot, and in fact, this level of oscillation is what they call ringing. Right, now this might give you an indication of a type of circuit that you might want this to happen. There are tone circuits, or like maybe even a simple doorbell, right? So a doorbell and a chime. You press it, the chime, which is the step at the bottom, so that's the push button there, and the system reacts, and it generates a little up-down oscillation here and eventually dies down. That's like a chime tone or a bell tone and so on. So if your circuits are musical applications, for argument's sake, something like this may well be applicable. In control engineering, in things like amplifiers and communication systems and the like, this sort of behavior is not acceptable, right? And so usually it will be confined to a very small field of special things like musical instruments and the like. All right, and then k equal to 0. So here's k equal to 0. The thing is oscillating all the time now, right? At this point in time, the resolution is kind of poor here, but it's a sinusoid. Remember the k equal to 0 inside of here. And if we go back to the expression here, right? If I put k equal to 0 inside of here, all right? So you have full oscillations going on inside of here, because if k equal to 0, then we're going to have an e to the minus j a naught t, right? We have a k is 0, k is 0 in these points here. So you could take off k here, right? So what you're going to be left with is e to the j omega t, right? Because you have a square root minus 1 inside of there. So that's going to give you oscillations inside of there, and it's going to go on in perpetuity. Right now, strangely enough, this is a type you could, it may be something that you want. This morning in electronics, we spoke about oscillators, particularly, well, the sinusoidal oscillators, and we saw we had to go through a lot of rigmarole to make one oscillate, which is to, with the various bridge networks and the like. But here it is now. If you have a system, and whatever is a second order system, and you make the behavior in such a way where this factor k is 0, that if you put a step into it, that the thing is going to oscillate. Remember, this is a step here. This is my step here. So put this step in, so like a little power switch, you just put the step in, and this thing is going to give you an oscillator here. So this is kind of the system behavior of what we were talking about this morning. And in fact, it's so common that we have standardized it. And the terminology now is that A0, A, which is what we had in the original expression, they've given it a standard terminology, which is omega 0, which is the natural or the resonant frequency of the system. K is something called the system damping factor. They sometimes use K, or there's a Greek letter zeta, right? So you'll see both of them appearing. The controls people use zeta a lot. So the standard form of that equation that we had before, that we started off with, which is this thing in yellow, right? K is zeta, A is omega, right? And of course, right, A would be the normal system gain. So if you go back, you remember what we had been saying in electronics, for instance, to make a second order system, you remember we had a bandpass, the Weinberg had a bandpass transfer function. But when you look at this part of it and compare it to what we had in the little circuit that we discussed, those of you who were in the electronics class, and you can see the comparisons here with the omega and how we derive the omega and so on. Same sort of second order function, and for those transfer functions, we remove the damping, right? So for an oscillator in electronics, we want to make the damping 0. When the damping is 0, the system oscillates all the time. And well, of course, the other criteria that we spoke about. But here's the other side of it. I told you that we look at it in a slightly different way. So in electronics, I gave it a transfer function, which is slightly different from this, but the denominator is the same structure. And I told you, okay, we make some assumptions here and we spoke about it, but here you're actually seeing why some of those assumptions work. All right, and how it is connected. So what happens in an oscillator in that case? They remove the damping factor, they make it 0, so the system has no choice but to oscillate. Okay, and in the case of controls and other engineering courses that you're going to meet, that the values of zeta, depending on the value, they have some terminologies for them. So when zeta is less than 1, they call the system underdamped, right? Underdamped means that it potentially can give you, when it's underdamped, and of course this thing mustn't go negative at all, when it's underdamped is when you get the oscillations and the overshoot. Remember the terms that we use, overshoot and oscillation and or oscillations, right? So when zeta, the damping factor, okay, is less than 1, the system is underdamped. When it is greater than 1, then the system is overdamped. That is when it behaves like a first order system. So it will rise, and of course, depending on the value of k or zeta, it will do this. So it doesn't have any overshoot, but it will vary how long it takes, how long the transient period is before it eventually gets into steady state. So too much damping is also bad depending on the type of application that you're dealing with. Certain types of applications, you may want the response to be very slow and steady. Other ones, it might be time critical, but you have something to consider. If for instance, this was a step response for a system, if you make it, if you try to get it to respond too fast, then the system, by trying to get it to respond too fast, so this is my step coming in. Let me just draw this step again. So this is a step coming in. If I try to make the system respond too fast, meaning that I make the damping small, then it has a tendency to do this, right? And it could do that, it could oscillate a lot more. So trying to get it to respond quickly, a second order system, you will get overshoot oscillations. Making it respond longer now means that the response time stretches out. You have to decide if the period that it stretches out for your particular application is worth it. Once you have set the damping to be greater than 1, we say that the system is overdamped. In other words, it always has a tendency to oscillate when we are really putting a lid on that. And then this particular one, when zeta is equal to 1, that is a point just before the overshooting occurs. So just at that point, it is right at the sort of threshold for overshooting, and that is what we call critically damped. Right now, that's a very borderline sort of case, and many applications they would go a little beyond that. So rather than making the system critically damped, they would go a little bit beyond. But critical is probably the fastest. Not is probably, critically would be the fastest response that you could get for a second order system for a step input without the system having overshoot. Yeah. So many times again, when you go to controls and you're going to do a lot more analysis on this, and there are some other restrictions that we'll see as we go through this course as well. But they will talk a lot about underdamped and overdamped and critically damped systems. And one of the things you have to remember is that we're dealing with these things on a sort of modular basis. But remember, this particular module that we were looking at here, that particular transfer function may just be a small part of a much bigger thing. So the output of this has to feed something else, which has to feed something else. Okay, so the response of each and every component has to be assessed, and then you look at what the overall response might be. When we start to discuss block diagrams next week, That is where you have, after you have decided what each and every component, the transfer functions of each and every one of them are, then you put it together now as a diagrammatic representation and try to simplify and see what the whole transfer function looks like. Luckily for us, we have some tools now to help us with that, and MATLAB, for us, at least in the engineering circles, MATLAB or Octave or Scilab, all three of them are quite similar, but they would allow you to model the system on a big systems, draw it out in a block diagram, and then see what happens, what the step response, what the other responses look like. Yeah. Right. So in most applications, yes, a little over damping would be preferred to critically damped. Right? Critically damped is right on the borderline. So what happens is that if parameters, you remember all of these, this is our model. So you're going back to real world components and parts to deal with. So if the system, if you have designed it to be critically damped, and your calculated values of components, when you put them into the system, that the calculated values vary a little bit. Most components have a tolerance value. Remember when we were talking about instrumentation amplifiers, we saw that a 5% tolerance resistor, the kind of damage that could have done to the common mode rejection ratio of the amplifier. So same sort of thing here. Components on real world parts and power supplies and so on have a certain variation. So if you design for exactly the borderline, then if something varies in the wrong direction, you're going to go from critically damped to underdamped, and you're going to have some oscillations coming in, right? So yes, as a general answer, you would try to probably be slightly overdamped, but in a big system design, you have to watch everybody else in the pipeline to see what's happening. Yeah. So questions. Questions on this? Everybody following? Remember, again, this is all using the S domain as the sort of the simulation platform for us. Remember, we're given what do you call it, a real system, and this system is described by a set of differential equations. It's very difficult to get this sort of behavior model. You can't ascertain a lot of this thing without having to solve the differential equation. But here in the Laplace domain, from varying it, we can immediately see, and we'll do more of that as we go along, right? Once we get into the Fourier domain and some of the stuff related there, to actually see what the other behavior in terms of like frequency and thing is concerned. But here's a general, this one now is serving as a general guide. So if you have a system or a part of a system that has turned out to have a second order transfer function looking like this, I'll just forget the excess, looking like that, then immediately from whatever the coefficients are inside of there, so you could go back to the example that we were dealing with, which was this one here, you could go right back to here, and depending on the values inside of there, right, you could say, you could play around with it right there without having to solve the equation for it, or getting back from S domain to time to see that how the system responds. All right. So questions? Right, we all right? Okay, so none right now. I'm sure as you think about it, or as other like problem set questions or past paper questions come up, you will have some things that we'll have to discuss. So keep that in mind. All right, so let me stop this recording for the time being here.